So last week we talked a little bit about inverse functions. We talked about exponential functions, and that sort of left us with an issue because if we need to, like, let's say that y is equal to 2 to the power of x, um, what happens if we need to solve for x? We know what the y coordinate is, but we want to know what the x coordinate is. That's a problem that we've been able to deal with for things like quadratics. It's something that we looked at for polynomials and rational functions. It's how we found x-intercepts, right? Um, and it turns out that sometimes this problem is relatively straightforward, right? If like 8 is equal to 2 to the power of x, then x has to be equal to 3, right? Because we know 8 is equal to 2 cubed. It's 2 times 2 times 2, right? But things are a little trickier if, say, 7 is equal to 2 to the power of x. That's harder, right? We know that x is probably going to be bigger than 2 because 7 is bigger than 2 squared, which is 4, right? And we know x will be less than 3 because 7 is less than 2 cubed, which is 8. But we don't know much about anything in between that. How do we estimate that? Well, we could do a bunch of guessing and checking stuff, but that seems really difficult. So instead, basically, math invented a function to deal with this. So uh, this is where the logarithm comes in. So let's let x and b be positive real numbers. With b not equal to 1, then y equals log base b of x is the logarithmic function with base b where log base b of x is the inverse of b to the power of x. This gives us two important definitions, okay? Or two important facts. So first off, one, when I say the definition of the logarithm, this is usually what I mean. But it's that y equals log base b of x is equivalent to b to the power of y is equal to x. Basically, this statement here, this fact that y equals log base b of x is equivalent to b to the y equals x, lets us rewrite exponential equations into a logarithmic form or rewrite logarithmic equations into an exponential form. And this is frequently useful to solve for the thing that's actually in the exponent. We'll look at that in just a second. The other thing is log base b of x is the inverse of b to the power of x. So that means that by the definition of the inverse function, if we compose the two, we should get the inside, right? So that means that log base b of b to the power of x is equal to x, and b to the power of log base b of x is also equal to x. In some sense, the logarithm and the exponential cancel each other out. A brief moment here, actually. This statement, as an aside, so I'm going to do this in. Let's go grab a different color. So typographically, log base b of b to the power of x. This b here, that is the base of your logarithm, this tells you what your base is. It goes in the basement here. This should be a subscript. And then we sort of take the logarithm of some thing, right? Log base b of blank. There's a hidden of here, right? And essentially, this is not multiplying. We're not multiplying log base b times something. There's no multiplication happening here. This is functional notation. It's log base b of stuff. Okay. And that stuff is on a regular line. And in particular, this log base b of b to the power of x, we had a superscript inside of the regular line. So something I see relatively commonly when people are first starting to deal with logarithms is that they want to they sort of move things around in weird ways, and they want their subscripts to be, or they don't write their subscripts, and it just gets a little confusing. So make sure that when you're stating a base for your logarithm, whatever this b is, then you're actually writing it in a subscript like that. Any questions so far about the definition of the logarithm or how to write them? Okay. So I assume everyone's happy and we can continue onwards. Um, so using logarithms, we can now answer, for example, if 2 to the power of x is equal to 7, then we can rewrite in log form. So we're using that definition of the logarithm that y equals log base b of x is equivalent to b to the y is equal to x. So if 2 to the x is equal to 7, that means that log base 2 of, let's see here, if 2 to the x is equal to 7 is equivalent to log base 2 of 7 is equal to x. And depending on your calculator, you might have be able to just evaluate that in your calculator straight up. Some calculators don't let you do this. But yeah, it looks like Desmos won't let me do that even. I'm sure that there's a way to do it. So in order to evaluate this, we need what's called the change of base formula. So that is log base b of x is equal to ln of let's come back to the change of base formula in a second, actually. Let's see if I can get it to. That's annoying. I was really hoping Desmos would be able to do that one for us. All right, the graphing version of Desmos will, at least. Okay. So not the scientific version, but the graphing one will. So log base 2 of 7 is about 2.807. Okay. So it is somewhere between 2 and 3, a little closer to 3 than 2, which makes sense. 7 is a little closer to 8 than. So there are a couple of special logarithms that we use often enough that we want to write them in a more brief way. There's what's called the common logarithm. And this is the logarithm with base 10. Okay, and the common logarithm is very common. You see it in a lot of science settings. For example, the common log is used in computing pH balance, the Richter scale for earthquakes, decibels for sound. And actually, what log base 10 of a number does, it actually tells you kind of how long that number is. It tells you sort of how many digits are in that number. When we write the common logarithm, log base 10 of x, we usually don't write the 10. So we usually just write log of x. So no base. So if you see a logarithm with no base in this class, you should assume that it is log base 10. It is the common logarithm. Okay, and so as an aside, log of x counts the number of digits in a number. For instance, if we take the number, let's say 1, 2, 3, 4, 5, 6, that's a 6-digit number, and then we take the log of that, it is 5.0915. So it's 6. Well, so it's 5 digits after the 1. So it is one more. So it counts the number of digits in the number minus 1. So if we did 1, 2, 3, 4, 5, 6, 7, for instance, then it becomes 6. If we go to 8, it becomes 7. If we go to 9, it becomes 8. Right. The decimal sort of tells you how big that number is within that. So, for instance, if we did 5 or 4, 2, 3, 4, 5, 6, 7, 8, 9, you'll notice that it's a bigger value of 8. If we do 8.2345 or 8, 2, 3, 4, 5, 6, 7, 8, 9, you'll notice that it's even bigger value of 8. It's 8.9 now. Okay. And basically, this gives us an insight into why logarithms are useful. In some sense, the human um, brain actually perceives a lot of things in the universe logarithmically. The example I always use for this, or the one that always stuck with me, is that when we count things, we tend to be able to count things based on percent differences. For instance, if you show people a picture of 10 jelly beans and 15 jelly beans, they'll be able to tell the difference between 10 jelly beans and 15 jelly beans. But if you show them a picture of 100 jelly beans and 105 jelly beans, no one's going to be able to tell the difference between them. You're going to get different statements on which one's lying, right? And similarly, if you are, a prehistoric human, the difference between one lion and two lions is extremely important, right? Knowing that there's one lion and knowing that there's two lions is a good thing to be aware of, right? The difference between 100 lions and 101 lions is not very important at all. You're still in a lot of trouble if there's 100 lions or 101 lions. Even though that absolute value difference of just one number, one lion, is the same between 1 and 2 and 100 and 101, somehow the percent change is very different. And that's a meaningful thing to human perspective. Um, we perceive sound in a similar way. Sound waves are measured with the amount of pressure of the sound, like the actual physical amount of pressure. But we perceive a sound that has 10 times as much pressure as being as being a little bit louder, right? So the logarithmic scale is more useful there. All right. There's another special logarithm, one more, which is called the natural logarithm. And this uses that number that came up in last class, e. Okay, the natural logarithm is the logarithm with base e. Okay, um, and the natural log, technically, the natural log can be used in basically any situation in which any other logarithm can be used in a lot of cases. And it's a really, it shows up a lot in differential equations and calculus, so a lot of physics situations. The natural log shows up in solutions. A lot of the things that we use logarithmic scales for were really actually like the original thing was written as a natural logarithm, like the relationship was found using a natural logarithm, and then we rewrote them to use log base 10 because we use a base 10 number system. um, the natural logarithm is e is a very important special thing, and it's an important logarithm to be able to be flexible with in calculus. It's the one logarithm that we actually need to know how to deal with in a calculus setting, and then all the other logarithms with different bases are developed from this logarithm. Um, so the logarithm with base e, um, we write log base e of x as ln x. And the I use the natural log a lot when I'm solving logarithmic equations and things, because it has two letters instead of three letters, so it's faster to write. Um, so I tend to use ln instead of log base 10. You can use log base 10 anywhere I use ln, and you should end up with a similar result, if not outright the same result. Actually, it should always be outright the same result eventually. Um, so, a quick caveat. So beware. Some sources use log x to mean ln of x. This is not the most common thing in the world, but it does show up, particularly in a lot of mathematics sources. So if you look at maybe older or higher level mathematics textbooks, or in particular, uh, so in particular, Wolfram Alpha, um, which is a sort of like it's kind of like a calculator website, but it's like the craziest, most powerful calculator in the world. It's kind of picky about what you put into it, but it gives you a lot of information about anything mathematical that you plug into it. But it does do some weird notation. It loves to spit out polynomials in reverse standard form. So instead of from the largest power of x, it goes to the smallest power of x. It tends to spit them out from the smallest power of x to the largest power of x. And it also writes log x instead of ln of x. So when it says log of x, it means log base e of x. In this class, I will always write log x to mean log base 10 of x, and log, or sorry, ln of x to be log base x. I will not switch between the two. So, notably, ln actually doesn't stand for. It's actually a French abbreviation. It stands for log natural instead of natural log, which is why it's ln instead of nl. Um, Fun facts. Okay, any questions about these two special logarithms, the common logarithm or the natural logarithm? They're basically just shorthand. They're logarithms that we want to use commonly enough or naturally enough that we just need to be able to write them in a quicker way. So if your calculator does not offer the option of evaluating logarithms with an arbitrary base. For instance, TI-83 and TI-84 calculators tend to let you do this. So like, for example, a TI-84 graphing calculator has log base as a function in the math menu. But the TI-30 calculators that I told you guys to grab for this class, the what are they, the 2XAs or something? It doesn't have this capability. Then we need what's called the change of base formula. Or if you're using a slide rule. If you're using a slide rule, you definitely need the change of base formula. But if you're using a slide rule, then you're, well, bless you. So the change of base formula lets us evaluate arbitrary logarithms using logarithms with a standard base. So it says basically, so the change of base formula says that log base b of x is equal to log of x divided by log b, or ln of x over ln of. Technically, you can use any base you want for this change of base formula. You could do log base 2 of x over log base 2 of b if you wanted to. But if your calculator can't deal with log base 5 of x, it probably can't deal with log base 2 of x either. So you probably want to use either the common or the natural log, which every single calculator that you would use for this class. So anything more sophisticated than a 4-function calculator should be able to do log and log natural, right? So in Desmos, the scientific version of Desmos that I've been using as my calculator since we switched to remote, you'll notice that ln and log are over here. So they are in here, but I was having trouble. I couldn't do log base 2 of x, right? Or log base 2 of 7. So if we want to evaluate, so for example, log base 2 of 7, then that would be log of 7 divided by log of 2. So that would be log of 7 divided by log of 2, which gives us that same 2.807 that we got before. And just to show that the natural log works as well, let's go ahead and use that version of it. So we can also do it as ln of 7 divided by ln of 2. So that's ln of 7 divided by ln of 2. So same thing. Okay. There are a couple of more very basic properties of logarithms. In particular, actually, let's just go ahead and hit them all at once. Let's go and talk about the properties of logarithms in general. So when we talked about exponential functions, we had a handful of properties. In particular, we had a product, quotient, and power property. And logarithms have related and similar product, quotient, and power properties. So first off, one product property. The product property of logarithms says that if we have the log base b of a product, x times y, then we can actually expand that into 2 logarithms and turn it into a sum. So that's log base b of x plus log base b of y. We also get a quotient property of logarithms, which predictably, if you have log base b of x divided by y, in the same way that with exponents, multiplication was related to addition and division was related to subtraction, we're going to get the same thing here. So x divided by y will give us log base b of x minus log base b of y. And then we get a power property. This is that if this is log base b of x to the power of y is equal to y times log base b x. So in the same way that previously exponents then got sort of related to multiplication, It happens here as well. If you have some power inside your logarithm, you can move that power out in front. We also get a identity property, which is that log base b of b is equal to 1. So in some sense, when you're taking log base b of something, if you're taking log with a base, right, it asks what power do I have to raise this base to get the number inside my argument, right? I'm taking log base b of something, then what power do I have to raise b to get that something? What power do I have to raise b to get itself? Well, if you do b to the power of 1, you get 1. Or sorry, if you do b to the power of 1, you get b. So your logarithm base b of b is 1. And we also have an annihilator property, which is that log base b of 1 is equal to 0. What power do I have to raise b to get 1? Well, b to the power of 0 is equal to 1. Anything to the power of 0 is, except for 0. 0 to the power of 0. These 5 properties are really important. The exponential properties that we did last class are also very important, but these ones in particular we're going to use a bunch in this unit. They're going to be one of the more important. So if nothing else makes it into your notes, this definitely should. I would almost put this in like a page and like dog ear it so that you can go back to it. So how can we use these properties? Well, we can use them to expand and condense logarithmic expressions. So for example, let's expand log base 3 of 9x squared over z squared y to the 4th. And when we say we want to expand a logarithmic expression, we're using these properties and we're going from the left side to the right side. Okay, we're taking a single logarithmic expression and writing it as a bunch of logarithmic expressions. This process is one of those things that feels really it doesn't make a ton of sense when you're doing it in college algebra because it feels like you're just making it messier. But if you were to sort of evaluate these things, you would want to evaluate them kind of one at a time. So it's nice to pull them out and sort of deal with them one by one. And then you can plug in your values as you see fit. It's also really important, again, in calculus. A lot of this 121 class is still sort of aimed at like, here are the tools you need for calculus. Expanding logarithms is something really important there. For those of you who are not on the track to calculus after this, we're going to do some stuff with logarithms that's extremely important in like statistical settings, particularly using logarithms to model things. Shows up a ton in statistics. So log base 3 of 9x squared over z squared y to the 4th, we can first apply a quotient property because we have a big quotient. We have 9x squared divided by z squared y to the 4th. So we get log base 3 of 9x squared, that's the numerator, minus log base 3 of z squared y to the 4th. We're just using that quotient property to split up our logarithms here. Actually, I'm going to go ahead and pull these properties up into this window here. Are those readable at all on the stream? Yes, no, maybe, someone?
A little bit, yeah. They're just small.
Okay. Let's see if I can make them a little bit bigger.
That works for me.
So we used our quotient property there. And then in each of these two parts of our quotient, our numerator and our denominator, we can use some product properties. So we get log base 3 of 9 plus log base 3 of x squared minus, and we're subtracting this entire denominator here. So I'm going to put parentheses around it. We get log base 3 of z squared plus log base 3 of y to the fourth. I'm going to distribute that negative sign real fast. Oh, that should be a minus. That's why I was distributing. Okay. Notice that anything that was in the denominator of your original logarithmic expression is going to be negative in your simplified version, or your expanded version, and anything that was in the numerator will be positive. We've got one more step that we can do to simplify some things. This log base 3 of 9 we can evaluate. And then these other three, x squared, z squared, y to the fourth, we can use a power property. Log base 3 of 9, what power do we have to raise 3 to be 9? Well, 3 squared is 9. So log base 3 of 9 is 2. Log base 3 of x squared, we can use our power property, that log base b of x to the power of y is y times log base b of x. So that's plus 2 times log base 3 of x minus 2 times log base 3 of z minus 4 times log base 3 y. And that's our final expanded answer. So when you're expanding logarithms, you kind of want to go, you're kind of doing it backwards, right? You're doing your quotients and your products first, in reverse order operations, the same way you do when you're solving any sort of equation. You're always sort of doing your steps in reverse order of operations, right? And then eventually, once you've gotten all your products and quotients taken care of, then you will deal with any powers. Okay. So there were a couple of properties that are important that I sort of skipped and I shouldn't have skipped. Let's put them in red quick. So log base b of 0 does not exist. You cannot take the logarithm of 0, okay? If we wanted to do log base 2 of 0, we would have to find some power that we would raise 2 to get 0. But there's nothing I can raise 2 to the power of, 2 to the power of 12, 2 to the power of negative 7. All of those are still positive numbers. There's nothing, so b to the power of x is never equal to 0. So log base b of 0 does not exist. And similarly, you cannot take the logarithm of a negative number. B to the power of x is always greater than 0. So log base b of x, if x is negative, does not exist. So if you're ever in a situation where you're being asked to take the logarithm of a 0 or a negative number, depending on what situation you're in, you maybe made a mistake earlier on, or the thing you're looking at doesn't exist, or you something is wrong. You should not be taking the logarithm of a negative number. That can't happen. All right. The other thing we can do with logarithms right now is sort of the opposite of expanding a logarithm. Instead of expanding the logarithm, we can also condense logarithms. Okay, so this one is actually going to be something that we'll use when solving logarithms a lot. Oftentimes, our strategy for solving logarithms or logarithmic equations is going to be to condense logarithms as much as possible, and then write them as one logarithm is equal to something else, and then rewrite it into an exponential form. Okay, so let's condense the following. Let's condense 2 ln x minus 4 ln y plus 2 ln z. Let's go back to our properties here so we have them. Okay. So when expanding logarithms, we went from left to right on our properties. When condensing logarithms, we're going to go from right to left. Okay. So 2 ln of x minus 4 ln of y plus 2 ln of z. The first thing we can do is we can use the power properties to give us ln of x squared minus ln of y to the fourth plus ln of z squared. Okay. Then we can use a quotient property to maybe condense these first two. So that's ln of x squared over y to the fourth plus ln of z squared. And then we can use a product property to get ln of x squared y to the fourth times z squared. Or alternatively, ln of x squared z squared over y to the fourth. Both are equivalent, right? Multiplying by z squared is multiplying by z squared over. So, note anything that was positive ended up in the numerator, right? So our positive ln of x squared ended up in the numerator. Our positive ln of z squared, the z squared ended up in the numerator. And anything that was negative ended up in the denominator. Ln of y to the fourth had a negative sign in front, so it ended up bottom. And the idea behind condensing logarithmic expressions is to write them in as in a single logarithmic expressions as possible. Okay, if possible. So one more quick caveat: um, ln of x plus y does not simplify. When I first started doing logarithms, I wanted this to turn into ln of x times ln of y, but that's the opposite direction. Okay, multiplication on the inside turns into addition on the outside. Addition on the inside doesn't turn into anything. Addition on the inside certainly doesn't turn into multiplication on the outside, right? Um, and it's and ln of x this is not equal to ln of x divided by ln of and also while we're at it so in particular let's actually do that backwards. Ln of x over ln of y is not equal to ln of x over y. And ln of x times ln of y is not equal to ln of x times y. If these two things were true, then we could just push things inside and outside of logarithms, right? But you can't just pull a logarithm out, okay? You can't distribute logarithms like that. Otherwise, we wouldn't have even talked about these properties in the first place, right? Um, ln of x over y is ln of x minus ln of y. So subtraction and division aren't the same thing, right? These are really common mistakes that I see. So I figured normally I would have just sort of caught those as they came up while you guys were working on them because I think it's important to see those mistakes and then get corrected on them. But since I don't get as much overview on what you guys are doing and I can't quite see exactly what you're working on as you work on things, this will have to do. So try and avoid these common mistakes. All right. I think that is probably enough content for today. Does anybody have any questions about the properties of logarithms that we went through, expanding and condensing them, evaluating simple logarithms? Okay. Um, so if that's the case, then I will drop off. I'll drop off a couple of examples for you guys to work on. Um, so so I will give you guys some problems. I'll also post an answer key for, or I'll give you guys an answer key for last week's activities. So if you want to check your work on those, and I will be hanging out in one of the voice channels. If you guys have any questions about what you're working on, or if you want to ask any questions in chat, I'll be happy to help out. And I will be hanging out on call for the next hour or so. So if you have any other questions or you want to talk to me about anything, feel free to pop in, and I'll be happy to chat with you about what. Um, but otherwise, let's go ahead and break out and start doing the activities.